Okay, good morning, everybody. Let's dive in. And let me start by congratulating you all. Finished all 10 assignments, right? Hooray. Okay. Now the bad news. Now our collective carbon footprint for this class will skyrocket. How many people have tried running this overnight on their machine? Not yet. Okay. Kind of. All right. So we apologize to Mother Nature. I apologize to your laptops. You're going to beat the heck out of them over the next month or so, but I promise you it will be worth it. So you are not at the end. You're at the end of the beginning. So hopefully at this point you have a stable code base. I want to just take a few minutes to talk a little bit about the assignments together, a couple things you can tune up to make sure everything is ticking over okay. And then we will dive in and start to talk about the final project and your first deliverable for the final project, which will be due as usual this coming Monday at 11:59 p.m. So you're still going to be submitting material to Blackboard every Monday night, but instead of the assignments, they're going to be weekly deliverables demonstrating to the TA and I that you're making steady progress towards your final project. We'll talk about that in a moment. Okay. Assignment 10, obviously all of you have very different laptops, very different platforms. Some laptops are older than others. We do our best in this course to make sure that we level the playing field as much as possible. So just as a disclaimer, from here on out, obviously we don't expect you to do X amount of evolutionary effort on your robot against your fitness function and so on. Whatever your laptop is capable of, that's fine. Some of you have already, I think, come up against the limits of your device. If you're running a population size of 10 for 10 generations using the quadruped, there is usually a pretty considerable memory requirement for that. Each individual simulation obviously has a larger number of links and joints and all sorts of things going on. So PyBullet, the physics engine that is underneath PyroSim, it will allocate more memory the larger and more complex you make your robot and its environment. So that takes up a fair bit of memory. And then, of course, you have 10 simulations running in parallel. And I saw some students in my office hours this week, and it was clearly too much for their laptop. So if you can't run 10 simulations in parallel, obviously that's no problem. You can scale it back. That's perfectly fine. You are free to tinker now with your code base. There are certain things you can do. You can still obviously run a population size of 10. You can run a population size of 100. You can just set a subset of the individuals in the population to run in parallel. So if you have a population size of 20, you can do 5 simulations in parallel and repeat that 3 more times to evaluate all individuals in the population. It's up to you how much or how little you want to parallelize your code, and obviously that's going to matter depending on your device. Okay, and then obviously the memory footprint of your individual simulation is going to matter. For some of you in your final project, you might want to try and create a relatively complicated environment for your robot to navigate. That's fine, just obviously keep an eye on how much that's taking up in terms of memory. Any questions about the assignments? Anything that's come up? Anything that's not clear? Okay. The amount of work for the first deliverable is not really that much. So there's a little bit of there's a little bit of breathing room in here for you between now and next Monday. So if you want to take some time, go back through your code base. We spent a fair bit of time halfway through refactoring your code so that it's a little bit more modular, hopefully a little bit more understandable. You got a fair bit of code there now. Hopefully most of it is fresh in your mind, but obviously 2 or 3 weeks from now, if you're working on other parts of your code base, it's easy to forget where things are in the underlying code. So feel free to take some time this week to also refactor, rename variables, rename classes, rename methods, clean things up, alphabetize things, make things clear and organized so that you can focus on the fun part of this course, which is doing your final project. All good? Anything else about the assignments? Okay. So let's talk about the final project. You'll notice there's a link to deliverable 1, and as I mentioned, this is due at 11:59 as usual next Monday. And if you scroll down to the bottom of the schedule, you'll now see there's a little bit more information about our exam period. There is no exam in this class. The night before the exam, you're going to be submitting some materials to Blackboard. We'll talk about those materials in a moment. Then on Tuesday, May 10th, bright and early, I don't set the exam times. We'll be here at 7:30 in the morning. We have 60 of you in this class. Might not feel like it this morning. We have 60 students in this class. You are all going to present your final project orally. We've got 60 presentations in a little less than 3 hours. So you're all going to have exactly 2 minutes and 30 seconds to present your class, to present your final project. Short and sweet. Okay. We're going to talk about the logistics about how that works in a moment. But just overview, you're submitting weekly deliverables, demonstrating progress towards your final project. You are submitting all your materials the night before the exam. There is no late extension on the submissions. If things are not submitted by 11:59 p.m., they will not be graded, because we're going to need those materials for the oral presentations the following morning at 7:30. Sound good? Okay. So the link behind the deliverable and the two links behind these two all lead to the same document. We're going to just skim through this morning just so that we're all literally on the same page. I highly recommend sometime this week you just sit down and read this document stem to stern. Everything is in here about what you need to know about the final project. Okay. As promised, you got a little bit over a month. There are exactly 42 days between now and the exam period. So you got 42 days to work on your final project. You have 4 weekly deliverables, the next 4 Mondays. And then the 5th Monday is the last week of class. No submission at that time. Between the submission of your 4th deliverable and you orally presenting or summarizing your final project, you got a little over 2 weeks. So sort of 4 weeks to ramp things up, then 2 weeks to work on this in earnest, present it orally on the 10th. Okay, you can see the grade breakdown here. Hopefully this all sums to 30%. Your final project is worth 30% of this course. Okay. Okay, so let's talk about the deliverables themselves. There are 2 kind of paths that you can follow towards the final project, the quote-unquote easy path and the quote-unquote hard path. I put those in quotes because they may or may not be easy depending on who you are. We have a very diverse crowd in this course. Some of you are much more comfortable coders than others. If you found the 10 assignments quite challenging, I recommend the easy path. If you enjoyed the assignments and you're ready to really dive in and try something more challenging, I recommend the hard path. For the graduate students that are here in this class, you're all following the hard path. Okay, so what's the easy path? If you click on the link here, it will take you to the second last module in our subreddit here, which is the final project itself. And you'll notice in the Reddit instructions, there's a whole list of various easy and hard projects. I've tried to give them all cutesy names here. Here's one easy project called Up, Up, and Away. This is altering the fitness function that selects for jumping rather than running. That's a relatively easy thing to do. It really only requires you to make a change to the fitness function, not really make any change to the rest of your code base. Let's see, Brainiac here. This is a harder project. This is complicating the neural controller of your robot, incorporating hidden neurons, incorporating central pattern generators, recurrent connections, self-connections. This project requires you to dive back into neural network.py and make some significant changes. Bodybuilding here. This is expanding your parallel hill climber, so that now it's not just optimizing the sets of synaptic weights in your neural controller, it's also optimizing aspects of the quadruped, like the length of the legs, possibly the number of legs. It's up to you. Each of these, you can think of these as prompts. They're continuations for each of these projects. Many worlds. evaluating your robot multiple times in different virtual environments and measuring its average performance or how well it does on average in those environments and so on. Okay. Again, you might want to scroll through and read these at your leisure sometime this week. So in the easy path, you can tackle each week a different easy project. Each easy project should take at most a week. The good thing about the easy path is if you get stuck at some point, obviously the next week you're starting fresh and on something else. The hard path, you're picking one of those hard projects and then breaking it down into at least 4 parts and implementing 1 part a week. Like the assignments, obviously the hard path is cumulative. Okay. There is no penalty for choosing the easy path over the hard path. I recommend, again, at this point, assessing your comfortability with coding and choosing the path that's best for you. Okay. If you choose the hard path, you can pick one of the hard projects listed in the subreddit, or you can also come up with one of your own. I've thrown out some ideas over the last several weeks about possible final project ideas. I'm sure many of you have some ideas of your own. Just shoot me an email or DM me on Teams, and we can go back and forth a little bit just to make sure that your idea is implementable in PyroSim and PyBullet, and that it's doable in about 6 weeks. Yeah? Okay. Any questions about that? Okay. Okay, so those are the first, those are the first 3 deliverables. 3, not 4. In the 4th deliverable, you're going to start in on what's known in engineering as an A/B test. You're going to be switching from implementation to analysis. So you're going to be implementing a couple of easy projects or 1 hard project. And then you're going to be performing an A/B test. You're going to take your code base at the end of the 3rd week and create 2 variations of that code base using 2 branches in GitHub. And those 2 variations or those 2 variants of your code are going to become A and B. You're going to do multiple independent evolutionary runs of A and B, and then compare the performance of those 2 algorithm variants. Did A produce a better robot, or did B produce a better robot, or was there no appreciable difference between those comparisons? We've actually seen many A/B tests in the experiments and projects we've talked about in this course so far, trying to determine whether something that was added to A to turn it into B actually helped or obstructed the evolutionary process. Just some examples of an A/B test you might tackle. These are popular projects that many students have tackled in past years. A involves involving a neural controller for a quadruped. B, evolve a controller with more or less the same architecture for the hexapod. Perform the same amount of evolutionary effort on both the quadruped and the hexapod. Which one evolves to move further? Yeah, that's an A/B test. You might replace the parallel hill climber with a more high-powered evolutionary algorithm. Strictly speaking, a parallel hill climber isn't really even an evolutionary algorithm. There's no crossover. I guess there's mutation in there, so it's somewhere on the fence. There are many, many more high-powered evolutionary algorithms. We're going to talk about two of them this week and next week. A popular project is obviously to rip out the parallel hill climber, replace it with another evolutionary algorithm, which becomes B. Compare A and B, where you're running 2 different evolutionary algorithms, but you're still running them for the same amount of computational effort. Your parallel hill climber at the moment performs 100 simulations, population size 10 for 10 generations. You can replace it with a different evolutionary algorithm. If you're going to compare them in an A/B test, you always have to compare apples to apples, not apples to oranges, right? If you're going to run these 2 different evolutionary algorithms, each of them should have the same computational budget. Each of them is only allowed to run 100 simulations, and then at the end, you're going to compare which of them produced the better robot. Yeah? Okay. You might include CPGs, or you might build out the brain of your robot. At the moment, it's still pretty minimal. We've talked a fair bit about different kinds of neurons, synapses, and what they may or may not afford to your robot. or what opportunities they may afford to the evolutionary process. That would be another A/B test with and without CPGs. Okay. At the end of deliverable 4, you're going to show us some proof that you've begun your A/B testing by performing one run of A, one run of B, and then submitting some visualizations from those 2 runs. That might be 2 different fitness curves. The end of deliverable 4, it doesn't matter whether those curves overlap. You're not going to have enough data at the end of the 4th week to actually conclude that A is better than B or vice versa. We just want to see that you have your 2 versions running and that you're starting to generate some visualizations from them. You might produce a footprint graph of the best robot from A and another footprint graph from the best robot from B, or a phylogenetic tree visualization, which we talked about last week, and so on. Again, just visual demonstration to us that you're making progress. Okay, that covers the next 4 weeks. So far, so good? Okay. In the exam period, when you're going to demonstrate your project orally to us in class, you're going to be talking over a YouTube video. We're going to have a YouTube playlist of 60 YouTube videos. You're not going to have a lot of time, so you're going to spend your 2.5 minutes telling us what you did, especially if you came up with your own project, describing a little bit about what that is, a video of the best robot from A, a video of the best robot from B, and then some visualizations trying to convince us that A produced better robots or B produced better robots, or there was no appreciable difference. Okay. From multiple runs of A and B. So those 2 weeks, weeks 5 and 6, assuming that your laptop can handle it, I assume that I would suggest that in the evening you set up a couple runs of A, let those run overnight, record those runs. The next night, do a couple runs of B. The next night, a couple runs of A. The more independent trials of A and the more independent trials of B you can collect in weeks 5 and 6, the better chance you're going to have of convincing yourself and convincing us that A is better, B is better, or that despite considerable computational effort on both, there doesn't seem to be a difference between them. Yeah? Okay. Okay, so let's talk about what you're doing over the next week. First deliverable, if you choose the easy project, pick one of them, implement it, and as always, submit one video demonstrating that it was achieved. I think in most of the descriptions, it doesn't actually describe what we want to see in that video, but I think you get the idea at this point. Make sure you capture the video in some way that it's pretty clear to us about what we're supposed to be seeing. You can type in a couple sentences of some explanation directly into Blackboard if you want. That's perfectly fine. Okay. Like all the assignments, upload your videos to YouTube and then just embed the YouTube link in a Reddit post. Embed the Reddit post link into Blackboard. You can also drop the YouTube link in there as well. That's fine. Okay. If you choose the hard project, you're still going to be submitting a video, but that video is going to demonstrate that you're 1/3 of the way towards completing that particular project. It's up to you to decide how to break this down into 3 bite-sized chunks. Just make sure, obviously, when you're submitting in Blackboard to describe to us in just a few sentences, we don't need a paragraph, we don't need an essay, about what your project is, what we should be seeing in the current video, what implementation detail is being shown this week, what deliverable you're planning for the following week, and then what you plan to do to complete the project. For example, one of the hard projects is changing your quadruped into a biped. Week 1, you might just show that you've built the biped. That's perfectly fine. That takes a little bit to do. Maybe the biped just falls over, but we should be able to see that all the links and joints are in the right place and the joint axes are where you would expect them to point and so on. That would be a reasonable first deliverable. Second deliverable, show us some attempts to evolve locomotion for your biped. If you remember the bipedal locomotion lecture, you're probably going to end up in the Ministry of Silly Walks. That's perfectly fine as a deliverable. It shows us at least that it's working. And then the third week, you might show us that you now have a biped that's able to take a couple of stable steps before falling over because you made some change to the fitness function that rewards displacement but penalizes silly walks, right? Deliverable 1, 2, 3. Yeah. Continuing the biped example, if you wanted to do an A/B test with the biped, try evolving gaits for a biped with arms and without arms. Yeah? Okay. Let's see. Okay, I just talked about that. There's another written example here for avoiding objects in the environment. So far, so good? Any questions? Okay. All right. Deliverable 2, you're doing the same thing. If you're choosing the easy path where you're doing 1-week projects each week, just pick another one, implement it, upload the video. If you evolved jumping the previous week, you might add to it by evolving pronking this week. So all of the easy projects are designed that you can basically start them from the quadruped with the parallel hill climber. You can always start them from the end of assignment 10, which you're free to do. You can always roll back your code each week and start again from assignment 10. But you can also stitch them together. So you can evolve jumping 1 week, pronking the next week, and then something else the week after that. It's up to you. Just again, drop us a couple sentences in Blackboard to let us know what you're up to. Okay. Deliverable 3, same thing again. We just talked about deliverable 4, which is A/B testing. Split it into the A and B variant. If you follow the easy path, some of the easy projects, they can actually serve as A and B. They're similar enough that you can compare them 1 to 1. You can also take one of the easy projects and on your own figure out how to make an A and B variant of that easy project, and that could become your A and B test. Okay. At the end of deliverable 4, as I mentioned, you're going to be submitting some visualizations to show us that you're now able to generate data from A and B. We're going to assume that a fitness curve is the default. It's the easiest way to show evolutionary progress. But I want you in deliverable 4 to also try and tackle some of the other visualizations we've seen in this course. I left the links here for you. We saw footprint graphs, phylogenetic trees. We saw a lot of examples of visualizing how well an evolved robot does when it's placed in environments that it's never seen during evolution. It's a robustness plot. That's fine too. For those of you that are interested in visualization and artistically inclined, you might come up with your own way of visualizing what is the robot doing and what is the evolutionary process doing. Okay, that takes us to the end of week 4. You then have about 2 weeks to actually run A and B many, many times, visualize and compare them. And at the end of week 6, the night before our exam period, you're going to be submitting 2 items to Blackboard, a written report and a 2.5-minute YouTube video. The written report is obviously going to be a report of the A/B testing, where you're going to do the same amount of computational effort for A and B. In this report, 4 pages, 4 sections, 1 page per section, more or less. We take points off for poor writing quality. If we can't understand what you're saying or it's sloppy writing, we're going to assume that the science underlying the report is also sloppy. Write well in your written report. Okay. First section should describe your goals. What project did you tackle? Why did you tackle that project? What was interesting about it? How did you then take that project and split it into an A and B variant? What is the one detail that differs between A and B? Why did you find that interesting? Was it something we discussed in one of the lectures? Is it something you came across in your own reading? Where did the idea for your A and your B come from? Okay. Second section is implementation details. We're not expecting a copy and paste of a page of code into the second page of the report. You can include some code snippets if you like. parts of your code that are particularly important. These might be parts of your code where A and B differs. A mixture of code snippets and the written word are probably a good way to go for this second section. Third section, results from the A and B test itself. Myself or the TA should be able to scan this third page and quickly determine, yes, you've convinced me, A did better, or B did better, and I know why. Or neither did better, and you have some explanation for why you think neither A nor B did better. Yeah? Question?
So, what do we present on the 10th for the final? Are we going to go over some of the stuff on our papers, or mostly just going to be the video that we...
It's only the video. The written report is for Krishna and myself. Okay. The oral video we will also grade, but you're going to talk over your video the following morning. Okay. But you're submitting both the written report and the video on the night of the 9th. Good? Okay. Okay, so yeah, third section, 1 page, use visualizations. Use whatever you need to do to convince us that one was better than the other, right? If you do 1 run of A and 1 run of B and you show 2 fitness curves and they kind of overlap, but one is a little bit higher than the other, I'm not going to believe you, right? You all know by now that if you do a second run of your parallel hill climber, you can get a very different result, right? So it's going to take at least multiple runs of both. Depending on your A and B, it may take more runs than less runs. It's up to you, yeah? Some of you have probably taken a stats course. How many have heard of error bars? Most of you. How many people know what a p-value is? Oh, pretty much everybody. Okay. Assuming you know what error bars are and p-values, go back and brush off your stats notes. Bring in whatever statistical muscle you need to try and prove to us and prove to you that A is better than B or vice versa. If you're not familiar with those concepts, that's perfectly fine. One of the nice things about evolutionary robotics and evolutionary computation is you can rely on compute. If you do enough runs of A and B, you're going to get enough curves of A and enough fitness curves of B that it'll become very clear over time which one is better than the other without error bars, without p-values. Yeah? Okay. Final section, fourth page of the report. You should demonstrate to us that you've thought carefully about your deliverables and your A and B testing. 6 weeks is not a lot of time to do a detailed investigation of evolutionary robotics. I know you're taking other courses, you got other things going on. I don't expect full-time effort on this over the next 6 weeks. You can make it up to us in the 4th page of the report, where you can talk about your ideas about what would happen if you had another year to work on this project. If I bought you time and materials in the Fab Lab so that you could try and do sim to real, how might that work for your project, right? We've covered a lot of ground in this course. You really haven't had an effort to digest that material and describe it back to us or use it as a foundation for thinking about where you might want to go with evolutionary robotics, assuming you had the time and inclination and budget to do so. That's what the final part of the report is for. We'd also like you to introspect a little bit on how this final project played out, what was surprisingly difficult and what was surprisingly easy. If you had another year to work on this project, how might you expand it? What new features would you want PyroSim to have? Obviously, PyroSim is pretty limited. There's only so many sensors and motors and kinds of things you can do in PyroSim. If I hired you a team of physics engine engineers to expand PyroSim and PyBullet to support your project, what would you ask those engineers to implement in PyBullet? Okay. Written report due Monday night at 11:59 p.m. Again, no extension on any late submissions. We need everything in. We have to start grading everything. We have to submit the final grades for this course less than 72 hours after the exam period. So please make sure to get everything in on time. I will make a place in Blackboard for you to submit. Make sure it's PDF, 4 pages, double spaced, 12-point font is fine. If you want to write more, we're more than happy to read it. This is the bare minimum. Any questions about that? Pretty straightforward? Okay. Let's talk about the oral presentation. Like the written report, it should also have these 4 sections, which is a lot of material to cover in 2.5 minutes. As you can probably imagine, the biggest challenge in the oral presentation is communicating clearly and succinctly and sufficiently, getting everything you want to communicate across to us in 2.5 minutes. Takes a little bit of doing. Okay. Part of your grade for the oral presentation will be clarity of communication. So if we see 57 slides flash by in 2.5 minutes, make sure you focus on not quantity, but quality. Okay. In the results section of the video, you're probably the easiest way, obviously, to communicate in this course is with video. So show a video of an evolved behavior, show a video of a random behavior. If we see those 2 videos, that should convince us that at least in A, if those 2 videos are coming from A, or at least in B, if those 2 videos are coming from B, that there's been evolutionary progress, right? That's one of the ways that the TA has been grading your parallel hill climber and hill climber, is that we can see an obvious difference between a random behavior and an evolved behavior. You might then want to show another pair of videos, which is the best robot from A and the best robot from B, and at least visually, anecdotally, we should be able to see that one or the other is better at whatever you're evolving your robot to do. Okay. You might also want to include some visualizations that you included in your written report in the oral presentation. Okay. Make sure that when you submit your video, there's no audio in your video. You are during our oral presentations, each of you is going to come up to the front of the course and front of the class. As your video runs, you are going to narrate over your video. You are not going to be controlling the playlist. It's just going to run. So practice, practice, practice. Okay. I guess by now you know how to capture a video from your laptop. Yep.
Okay, so if you chose like the easy path and so
Yep.
you did like 3 different projects and
Yep.
then you chose like one split up into A and B.
Yes.
In the like presentation, do you want us to like mostly like just mention maybe like the first 2 and then mostly focus on the A and B? Or like not even mention like your other ones?
Yeah, great point. So if you do the easy project, you're going to have 3 projects, plus one of them has been split into A and B, so you kind of have 4 projects. It's up to you. That's perfectly fine. You could spend the first 30 seconds saying, in weeks 1 and 2, I did the jump and I did the pronk. There it is.
Okay.
30 seconds done. On to, I took pronking and I split pronking into A and B. There's random, there's A pronking, there's B pronking, and off you go.
Okay.
It's fine. Either's fine. Yep. Okay. Again, 2.5 minutes is not a lot of time. Feel free to include your bloopers as well. We have as you can imagine in my lab, we have a very, very long blooper reel. Perverse instantiation raises its ugly head everywhere and always. If you have time, for sure, include some bloopers. No problem. Okay. Okay, screen cap, yeah, but make sure your video is clear. Obviously, this is not a media studies class. We don't need super fancy graphics. As long as we can see what you're describing, when you say, there you can see there's no pronking, on the right you can see there's pronking, as long as we can see it in the video, that's perfectly fine. You might want to show your evolutionary algorithm running. We've done lots of scrolling of numbers. We all now know collectively how to read off a hill climber and see by the numbers whether it's making progress. You can include that as well as evidence. That's perfectly fine. Just make sure that it's reasonable that all of us can see the numbers in your video. When you're shooting your video, remember that you're directly in front of your screen and you're looking at what's on the screen. As you're capturing that, take, 30, 40 steps back. And if you can still see it on a relatively large screen, it'll show up just fine here. Yeah? Okay. So by the night before the exam period, make sure you upload your video to YouTube. Make sure the link is public. Make sure it's not for kids. Make sure it's all published on YouTube just fine. You're going to be submitting by midnight, by 11:59 p.m. between 11:59 p.m. and 7:30 a.m., the TA is going to stitch 60 videos together into a playlist. Poor Krishna, please bring him some coffee, assuming he's a caffeine person. It's a bit of a tough gig. So if he gets to your video at 2:30 in the morning and he can't find it, it's in the wrong format, there's audio, he's going to skip over it and go to the next one. So please make sure it's ready to go. Make sure it's exactly 2 minutes and 30 seconds. If it's 2 minutes and 29 seconds or 2 minutes and 31 seconds, that's fine. But even 2:35, 2:43, it's too long. We got 60 to get through. If Krishna sees that it's 2:45, he will skip over it, not include it in the playlist, and go on to the next video in the playlist. Yeah? Okay. Yes?
If we're at like 2:20, is that fine?
2:20 is fine. Yeah, absolutely. You can guess, though, that we're going to wonder that there's probably something useful you could have done with that last 10 seconds. 2:30 is not a lot of time. Make good use of your 2 minutes and 30 seconds. Yeah? Okay. I'm going to cross my fingers now. We've done this many, many years in the past. It's worked every time. But as you can probably get a sense now, this is a locomotive that's going to start picking up speed the night before. And once it starts moving, it's not slowing down, right? So please do your best to make sure you're putting your best foot forward. You're helping the TA, you're helping all of us so that this all runs smoothly. I guarantee you this will be the most fun exam period you've ever had. You're going to see a lot of great projects over these 2 hours and 45 minutes. But please do your best to help us make sure everything runs smoothly. Okay. Okay, I think I said all that. If you're late, 0%. We will all, oh yeah, okay. So we're all going to meet here in class. Please be sure to be here on time. At 7:30, I will upload to the schedule. I'll upload to the schedule the oral presentation schedule. You may be presenting first, you may be presenting last, so please make sure you're here well before 7:30, because if you're first, you're starting us off at 7:30. Obviously, if you present early, there's no necessarily reason for you to stay. As I mentioned, you all are going to do some amazing work. Please demonstrate some collegiality and respect for your fellow students by staying for the full period. I guarantee you it's going to be a fun show. Okay. At 7:30, I will press play on my machine on the playlist that Krishna has created. You can bring your devices to class. You can open your device. You'll see the presentation schedule. We will allow that playlist to run. And again, assuming everything goes well, we are not going to stop the playlist. If all goes well, the playlist should be exactly 2 hours and 45 minutes. I will build into the playlist 2 or 3 10-minute breaks so we can all get up and stretch our legs. Perfectly fine. Let's see. Okay, I'll make the presentation available. When the student before you begins speaking, you will come up to the front of the class and stand perhaps just over there. So you're on deck, ready to go. When the student here finishes presenting, the student will sit down. Your video will immediately come up. The moment you see your video, you start speaking, and off you go. Yeah? Okay. Okay, I think I said all that. If you run long in your oral presentation, if you're still speaking when your video ends, you're going to get the hook and the next student starts. So again, 2 minutes and 30 seconds is not a lot of time. The good news is you can practice 10 times in a row in half an hour. So when you submit or when you've got your video, practice, practice, practice. And it won't take that long. It'll take about an hour if you practice enough that you'll get down the timing so that you will finish at exactly 2 minutes and 30 seconds. This is also great practice for a couple of years from now when you're invited to give a TED Talk. They are extremely militant about timing and pacing as well. If you run long on your TED Talk, they shut off the mic and they shut off the lights. So good practice for your TED Talk. Okay. You're going to see a lot of amazing material. You're probably going to have lots of questions or ideas of your own. I wish we had more time for a Q&A session. We're not going to have time to field questions. If you see a cool, interesting project and you have questions, find your fellow student during the 10-minute break, ask your question, follow up with them after the exam period. Hopefully some of these projects are just the beginning of some discussions and collaborations. Please feel free to ask questions and interact with one another. Okay. Okay, collegiality, last thing about this. Obviously 2 hours and 45 minutes is a long time to be here. You're all going to have your devices. There will be the temptation, of course, to just tune out. Please show your fellow students some respect by being tuned in and learning something about all the various projects you're going to see in this course. Okay. It's a lot of material I just threw at you. Hopefully everything is there. Please read through this document again at your leisure. If you have any questions, just bring them back to class and we can discuss. All good? Okay. So back to lectures. Where were we and where are we going? We're working our way through open challenges in the field, and we're partway through crossing the reality gap, arguably the biggest open problem in the field. We looked at the envelope of noise hypothesis, sprinkle noise in a simulator so that evolution cannot overly exploit inaccuracies or approximations in the simulator. We got partway through the Golem project last time, which took a very different approach to the sim-to-real problem, which is attach your physics engine to this newfangled device known as a 3D printer and just sim-to-real as many diverse evolved robots as possible, and hopefully some of them will cross the reality gap. Arguably the biggest advantage of evolutionary approaches over all other branches of AI is they produce not just one good solution, but a diversity of solutions. And there is strength in diversity in many ways. One of them is, of course, diversity in terms of increasing the probability of crossing the sim-to-real gap. Yeah. We looked at the evolutionary algorithm they used in the Golem project, which is modifying both body and brain. We looked at the different mutation operators that make changes to body and brain during the evolutionary process. We looked at some of the diversity of forms that evolved in simulation. We looked at the phylogenetic tree last time, diversity in terms of evolutionary dynamics, divergence of species, convergence of species, emergence of species, extinction. And we ended last time by looking at 3 attempts to cross the gap. 2 failed, 1 worked particularly well, which raises the question of what is it about this particular design that allowed it to cross better than others. We're going to look at, in 2 lectures from now, we're going to look at the transferability project, which deals much more with discovering the features that allow things to transfer from simulation to reality. How might we know in simulation, before we transfer it to reality, how transferable that particular solution is? We talked a little bit about 3D printing, which in the year 2000, state-of-the-art was printing thermoplastic, which has a relatively low melting point. You extrude some liquid plastic, it quickly solidifies, and layer by layer you can build up the bones of the robot and then snap in all the rest of the electronics. And we ended with reduce, reuse, and recycle last time. Okay. Couple of miscellaneous points I want to make. These are just kind of historical observations. As I mentioned, in 2000, this was just the beginning of 3D printers entering academic labs. And there was a vision at that time. One of which became the Fab at Home project, which was to try and allow people to build their own 3D printer. So you could either order these parts and build them at home. And this project and a couple other ones around this time sort of kicked off the maker subculture, that you could make your own 3D printer and then hack and print your own kinds of devices at home, in your school, at your library, and so on. So for those that are kind of interested in hacker culture and Fab Labs, I recommend going to YouTube and checking out the full Fab at Home project. The Fab at Home project came out of the Lipson Lab, which is where the Golem project was done. So the Golem project and Fab at Home were done at the same time in the same lab. So it's the sort of same ideas cooking at that time. Okay. At the same time, and I'm going to play this without audio. You can go listen to this at home. This is the RepRap project that was conducted at the same time in the UK. RepRap project was very similar to Fab at Home. The idea was to try and make a 3D printer out of very simple parts that anybody would have access to. The twist of the RepRap project is that this particular 3D printer can print most of its own parts. Yeah? For fun, imagine you were to wrap the RepRap project in an evolutionary algorithm where you want to evolve a 3D printer, you want to evolve the design of a 3D printer to maximize various features of the RepRap 3D printer. What might some of those features be?
How much of it is actually reproducible on a machine?
Absolutely. So I think this is actually a relatively recent video. The first one, I think they could print like 40%. The RepRap could print 40% of its own parts. I'm not sure how many they've got to now. It's not quite 100%, but they're closing in on 100%, right? So you could evolve the design itself to try and close this loop. What other features of a not quite self-replicating machine, but a 3D printer that prints 3D printer parts, what other features might you want to maximize in an evolutionary design system?
You minimize the material.
Minimize the material, absolutely. So all of the parts that make up this, there's a lot of this waste material for sure. Efficiency, material efficiency. What else? So this 3D printer prints its own parts, but it doesn't assemble those parts. What other features might you want?
Maybe minimize the number of separate parts required so that there's less assembly required.
Absolutely, right? So minimize the number of parts or maximize the ease of assembly. Make it easy on us poor human slaves to build the next generation of RepRap. Obviously, it would be purely an academic exercise to make RepRaps that make RepRaps or evolve RepRaps that make RepRaps. It would be nice if a RepRap also makes useful things in addition to other RepRaps. So we could include some other features or terms in our fitness function so that it's able to print other useful things. What if we wanted it to print or manufacture very large things? We could evolve RepRaps that produce parts for a RepRap that's 10% larger than the RepRap that produced its own parts. Or a RepRap that's 10% smaller than the RepRap that printed those RepRap parts. Yeah? None of these things have been done, sort of food for thought, but I definitely think these are things that are going to be tackled in the next few years as 3D printing becomes easier, becomes more automatable, and becomes subjected to evolutionary or other kinds of AI-driven design systems. Yeah? Okay, not quite evolutionary robotics, but kind of an emerging sister discipline. That's the Golem project. Any questions about that before we push on? No? Okay, great. We're a little bit ahead of schedule. So for your consideration, I'm going to walk you through one of my own attempts to cross the sim to real gap. This has become known as the Resilient Machines Project. Okay. I'm going to skip ahead a little bit. I'm going to skip over the first few slides and just focus on the evolutionary robotics side of this project. When we did this project, this was in 2006, so this was conducted 6 years after the Golem project. I was a postdoc at that time. I had just finished my PhD. I knew about the Golem project by Hod Lipson. I joined Hod Lipson, who is now at Cornell University, and we returned to this question of the sim-to-real gap. But we returned to the sim-to-real gap problem from a different direction, and I'll talk about that in a moment. At that time, there were 3 approaches to evolutionary robotics, which we've all seen at this point. In the pre-physics engine age, there were a couple attempts in the 90s to just evolve controllers directly on physical robots. The obvious advantage, very simple. We don't need a physics engine. The evolutionary algorithm isn't going to glom on to details of the simulator that don't exist in reality. There is no sim-to-real gap. The obvious disadvantage is it requires hundreds or thousands or millions of trials on a physical machine. It is physically exhausting and takes a long period of time to carry out these kinds of experiments. And usually you end up beating the physical machine into the ground long before anything interesting evolves. Number 2, this is what we've seen most of in this course. This is the sort of standard approach. Create a simulation of the robot and its environment, evolve in sim, cross your fingers, and try and cross the gap. 2 obvious problems: the gap itself, and obviously it requires a human to handcraft the simulator. You all now have first-hand experience with how difficult it is to get a simulation right. Even for a 3-part robot that exists in a minimal environment where there's nothing except perfectly flat ground. You complicate the simulated environment, or you complicated the simulated robot, and things get very difficult very quickly, as I'm sure you all now have some experience with. Okay. The other approach, which we haven't seen too much of, this is tricky to get right, is we adapt a controller on the physical robot a bit to sort of get things started, and then allow the evolutionary process to take over. It's very difficult because it's very difficult to handcraft a controller. Yeah, again, hopefully you have some experience with that. Okay, so the Resilient Machines project introduced, it was an attempt to cross the sim-to-real gap, but it became a 4th way to do evolutionary robotics, which is not to create a simulator by hand, but to bring in a second evolutionary algorithm. This second evolutionary algorithm is not going to be evolving the robot or evolving the synaptic weights for the robot. It's evolving the simulator itself. I'm going to show you details of how exactly we did this in a moment. But given your experience with physics engines now, what features of a physics engine might you try and evolve so that that physics engine is more accurate and therefore increases the probability that the other evolutionary algorithm evolves robots that transfer from the evolved simulator to reality? What features of that simulation might you want to try and evolve to improve its accuracy?
Nice generalized surface friction or something.
Okay, so friction is usually at the top of the list. This is super hard to get right. We've actually hidden the details of how you specify friction and surface features in PyBullet. You can take all of those parameters and all those features, and we can add them to our genome. We can evolve the friction parameters of the simulator. What else? Collisions, yep. Again, really hard to get right. When we talked about collision detection and resolution, depending on the physics engine, there's lots of different parameters that describe how collisions are detected and how they're resolved. You can turn that over to evolutionary algorithms. Getting those parameters right is a very non-intuitive process, very difficult, perfect candidate to hand over to an AI system. What else? Friction, collisions.
Maybe the frequency of time steps.
Frequency of time steps, getting the amount of time that elapses from one time step to the next, super, super hard to get right. If you have a simple simulation, you can get away with big jumps, and you can do a lot of physics in a relatively short amount of computational time. As that simulation becomes more complicated, you need to shrink the time step to make sure everything is accurate. but how much to shrink it, very, very difficult to know how to do. There is a math course here called Numerical Methods. Has anyone taken that class? There's a fair bit of effort that goes in that class to actually talking about time steps. There are algorithms that will try and dynamically shrink and expand the time step depending on what's going on in the physical simulator. But again, difficult to get right. Okay, you can probably think of some other features of a simulator that you might subjugate to evolutionary control. What would be the fitness of a given simulator? We take a genome from this evolutionary algorithm, we pull out some numbers to set the friction parameters, we pull out some other numbers to guide how collision detection and resolution happens. We run the simulator. What's the fitness of the simulator?
Is it how maybe we put sensors on the actual robot and measure like how accurate the inputs and outputs are?
Absolutely. So I think what you're describing and what we're going to talk about in a moment is not sim to real, but real to sim. So you're going to see a physical robot in a moment, the resilient machine, that is going to collect real sensor data, and it's going to send that sensor data back into this evolutionary algorithm that is evolving physics engines. And the fitness function is going to be how closely virtual sensor data matches physical sensor data. Yeah? So if the virtual robot experiences the same kind of thing that the physical robot experiences in its virtual world, the virtual world is probably a better reflection of reality. Make sense? Okay. We have two evolutionary algorithms that are going to be running. We kind of nicknamed them in this project estimation and exploration. Estimation, because this evolutionary algorithm is trying to estimate reality and capture that in an accurate simulator. That's the estimate in estimation. We called the second evolutionary algorithm exploration because it's exploring all the different ways in which it can get the robot to do whatever we want it to do. Yeah? So sort of the technical name that we published this result under was the estimation exploration algorithm. Got these two evolutionary algorithms working together. One is evolving simulators. The other one is evolving sets of synaptic weights to control a robot. Okay. Let's have a look at the details of how exactly this works. I probably won't have a chance to finish this today. We'll start on this. I'm going to walk you through one run of the estimation exploration algorithm. We're going to start with our physical robot here. You've probably seen this body plan quite a few times by now. We've got our quadruped robot. It is not bilaterally symmetric like quadrupeds are in reality. It is radially symmetric all the way around. 4 legs, each one has an upper and lower part. So we have 9 main parts, and we have 8 rotational joints, 1 in each of the shoulder, 1 in each of the knees, and 8 motors controlling those 8 rotational joints, right? Exactly what you just finished doing in simulation. Okay. Instead of creating a virtual version of this robot in a physics engine, we started with an empty physics engine, and we told the estimation algorithm, we told the first of these 2 evolutionary algorithms, we gave it a bit of a hint. We said, the robot is made up of these 9 parts, but you figure out how they're put together, and you figure out how this thing operates in its environment. So this is kind of another example of a minimal simulation. We're trying to actually save ourselves the effort of creating a detailed simulation of this robot. We want the estimation algorithm to figure this out. It's supposed to be evolving simulations of this thing. So far, so good? Okay. Okay, so at this moment in time, we have this physical robot, and this is what this robot knows. So we're actually starting with real. We're going to do real to sim first, then we're going to do sim to real. We have this robot. It quote-unquote knows that it's made up of 9 parts and 8 motors, but it has no idea how those parts and those motors are arranged together. This robot has no camera on board. It can't see itself. It actually has only 2 sensors, and these are vestibular sensors. I think we talked about the vestibular sense before. What's a vestibular sensor? Or what does a vestibular sensor record? You have 2 of them.
Kind of like orientation or balance.
Orientation, right? In your inner ear. In our case, it tells us how our head is oriented relative to gravity. In the case of the robot here, there are 2 vestibular sensors, one that records the angle of the main body, left and right, so the centerpiece, how much it's tilted left and right, and a second vestibular sensor which reports how much this main body is tilted forward and back. So far, so good? Okay. Imagine for a moment that you are this robot. You're inside this main body. You're in this dark control room, and there are 8 levers in front of you, and these 8 levers control these 8 motors. You pull the lever, and it will flex the motor. Remember, flex is always rotate in, and if you push the lever forward, it's extend the motor or extend the joint outward. There's no camera, you can't see outside of this room, but you start pulling on these levers and you feel how much the control room tilts left and right and how much the control room tilts forward and backwards. I'm trying to give you a sense of the proximal view of the robot, right? We're trying to see the world through the robot's point of view, not the distal view, which is this. At the beginning of this experiment, the robot needs to build an accurate simulation of itself. It doesn't have a good sense of itself. We haven't even got close to the robot evolving to do what we want it to do, which is locomotion. Not even there yet. The robot is trying to build a simulation of itself. So the robot performs a random motor primitive, which we've talked about before, a relatively simple action. In this case, it simply extends some of the motors and flex some of the motors. In this case, it's flexing motor 1 and 5. We can see from the outside that motor 1 is the left shoulder and motor 5 is the left knee. It flexes those inward and downward, and all the others rotate upwards and outward. And the robot senses that it tilts to the right. What can the robot conclude from that? What would you conclude if you were inside this dark control room and you pulled on levers 1 and 5 and pushed all the rest away from you and the control room tilts to the right? That you were responsible for it. Good. Yep. So we'll go back to BabyBot for a moment. You made this happen. You can conclude that motors 1 and 5 are on the left, right? You tilted to the right. If things are flexing in and toward, when you pull the levers in, and when you push levers away, everything else flexes out and away. The conclusion is that motors 1 and 5, wherever they are, they must be somewhere on the left side of the body. Yeah? Everybody see that? Okay, so here's the robot. So the robot now has a little bit of real. It has one piece of data. Motor 1 and 5 down, tilt 20 degrees to the right. We're now going to watch the estimation algorithm do its thing. It is going to start evolving populations of simulations. Each one of these simulations, kind of colloquially, is the robot's current guess of how it's put together. How's the robot doing so far? Not so well, right? Not very accurate simulations. If you watch carefully towards the end of this video, you'll notice that the green block is always rotating about 20 degrees away from us, away from the viewer. This is the robot doing its job and me doing a poor job of cinematography here. I put the virtual camera in the wrong place. My apologies. When you watch this video, mentally rotate it 90 degrees. What you should be seeing is that this green block is always rotating 20 degrees to its right in exactly the same way that the physical robot did. Everybody get that? Okay, my apologies for the poor camera work here. Interestingly, you'll notice that at this point, the estimation algorithm has said, great, I've done real to sim. I found not just one simulation, but many simulations that explain reality so far. Maybe I'm put together like this, maybe I'm put together like this, maybe I'm put together like that. All of these explain reality. Okay, the robot's kind of in trouble at this point, right? It's done real to sim. From the point of view of the estimation algorithm, its job is done. It has an accurate simulation. What should the robot do next?
Try a different movement.
Try a different movement, right? We're going to assume, or we kind of told the robot, that it's physically, it's impossible for you to have different body plans simultaneously. So we kind of gave it, again, another hint by saying, you can't stop this process. You're not allowed to stop the estimation exploration algorithm until you have only one body plan or only one simulation that explains all of reality. So at this point, the robot at least knows that it doesn't have enough real yet to attempt sim to real. So the physical robot performs another action. In this case, it rotates, I forget which motors these were, 3 and 6. And in this case, it rotates about 10 degrees to the left. So now the physical robot has two pieces of data. When I did this, I got this sensory repercussion. When I did that, I got this sensory repercussion, right? The resilient machine here is doing embodied cognition. It is literally pushing against the world and observing how the world pushes back. Yeah? Okay. We're going to now start up the estimation algorithm again, and it's going to try and evolve simulators, and it's going to evaluate each simulator twice. In the first evaluation, it's going to rotate motors 1 and 6 down. Then it's going to play back that body plan or that simulation again, but rotate motors 3 and 6 down. And it's going to get back two pieces of virtual vestibular data. It already has 2 pieces of physical vestibular data, and it's going to take the difference between both. And a good simulator should be able to reproduce the vestibular sensation in both cases. Question?
When you're simulating multiple actions, does the robot carry over like the best ones from the worst ones that like match?
Yes.
Bring over the second one and then.
Absolutely, absolutely. So the way this estimation algorithm works is we evolve for a while, pause the evolutionary algorithm, allow the physical robot to do something, and then unpause the algorithm and keep going with its current guess of the simulators. We have the same population. The only difference we're making to the estimation algorithm when we unpause it is the way we compute fitness. Right? We're going to evaluate every simulation one additional time, and it has to try and explain that new piece of data plus all the original pieces of data.
How is that final evolved model housed in the robot?
What do you mean by housed in the robot?
Like, how is that stored in memory to the point where it's useful down the road?
Good question. So in 2006, we could not run this on board the robot. So we were just communicating to an off-board device. Once it has an accurate simulator, we're going to do what we normally do in evolutionary robotics. We're going to use that evolved simulator to evolve neural controllers off-board, not on the physical robot, and then send the best evolved neural controller to the physical robot. You can probably guess what the punchline is going to be, which is that sim to real becomes more successful the more of this we do. The more we allow evolution to produce a more accurate simulator, when we then move on to sim to real, we're more likely to transfer things from sim to real. But this was all done off-board the robot. If you did this today, you could probably run all of this on board the robot. Question?
And is this also involving things like the friction, or is it just the body plan?
Yeah, good question. So this was the first of a series of experiments. This was the first one, in which case we didn't evolve friction or anything. The only aspect of the simulation that we're evolving is the stuff in the simulator, the positions and orientations of the links and joints and so on. Yeah. Any other questions? Okay. So we're alternating back and forth between evolving simulations and getting some more data from the real world. I've shown you real to sim. This was our second real, and this is not our second sim. I'm going to jump ahead now to 8 cycles. So I'm going to start this video in a moment. And at this point in the experiment, the physical robot had performed 8 different actions. And we had done 7 different segments. We had run the estimation algorithm for 7 different times. And the reason I'm showing you the 8th one is at the beginning of the 8th round of estimation, the robot still doesn't understand itself very well until it does. So at this point, and I'll play this video. I don't know if I can put this. Oh, I can put this on loop. Okay. At this point in the experiment, each simulation is being played 8 times, and it is trying to match virtual vestibular data against physical vestibular data from each of those 8 physical trials. At this point, these poor simulations were probably matching the previous 7 actions, and they weren't doing a good job of explaining this new 8th action. And so at this point in the evolutionary trial, certain simulations started to mutate and evolve to explain all 7 plus the 8th trial. You'll notice for a very brief period of time, there's a simulation in which 3 legs are correct. 3 legs are correct, but the red leg is wrong. So that was kind of explaining 7.5 bits of information from reality. And a mutation then occurred that moved the leg. And suddenly that simulation was explaining most of the data from these 8 trials. Yeah?
How are you determining what to keep as like what was a proper fitness for a previous movement?
We're keeping all the movements, and whichever's we have a population of evolving simulations. So the simulations that are being deleted are the ones that explain less physical data than others in the population. The ones that are able to explain or match virtual and physical vestibular data better, those survive and produce slightly modified copies of themselves. Does that answer your question?
I think so. Many questions.
Many questions. Keep them coming, Jordan.
As you're just playing like one action, because it looks like it's trying to evolve the same.
Yeah, sorry. So you're right. So I've kind of tried to clean up this video a little bit. You're seeing the 8th action here. Each of the simulations that's flashing by, there were an additional 7 trials with that simulation that you're not seeing. Yep.
Could what has evolved for the 8th action like counteract what you evolved for the 7th action? Previous or?
Okay, that's a good question, and I'll come back to that. I think I know what this question is getting at. For the moment, we have just these 2 evolutionary algorithms, evolving accurate simulators, and the second one, which is going to evolve controllers for us in a moment. What I've deliberately not mentioned yet is how the robot is choosing what action to perform. We've got 1 minute left, so I won't have time to tell you how the robot chooses. It may look, if you go back and look at these slides and look at these actions, it might look like the robot is performing these actions at random. If you ever have the opportunity to watch a human baby does what psychologists refer to as motor babbling. It looks like the baby is just moving at random as well. There's still many in developmental psychology to believe that that is what babies are doing, that they're moving randomly. That is not what the resilient machine is doing. The resilient machine does not, whenever it's allowed to perform a new physical action, it doesn't perform a new random action. It turns out there's a smarter thing that you can do other than performing a random action. We're out of time. I'll leave you to think about what that might be. You have a quiz due tonight. You're starting in on the first deliverable of your final project. See you on Thursday. Have a good day.